Chemical ecology is the study of chemically mediated interactions between living species, as well as the implications of such interactions on the demography, behavior, and evolution of the animals and plants involved. As a result, it is a huge and highly multidisciplinary area. In this video, I'm going to present you the chemical principles existing behind most common LCA midpoint indicators. In the case you wish further personalized training or you wish to contact me for any other reason, feel free to reach out through my webpage sergiarfelis.com or through my social media. Here you have the index 1 will follow next. We will talk about the nitrogen and water cycles, terrestrial and water eutrophication, stratospheric and tropospheric ozone, human toxicity, fine particles, depletion of resources and land use. The nitrogen cycle is the transformation of the inert nitrogen that we have in the atmosphere through different biological, physical, and geological processes to more usable forms for living organisms. Most of the nitrogen on the planet is in the form of molecular or inorganic nitrogen in the air. This is the 78%, and only certain bacteria can convert nitrogen into biological molecules. Nitrogen is an essential element for all living things. This nitrogen is present in animals and plants and is released when they die. For instance, nitrogen is a building block of biological molecules such as proteins. It forms other components of the cells. In addition, it helps plants to synthesize chlorophyll. Nitrogen undergoes various types of transformation to maintain a balance in the ecosystem. Humans are also interfering with the nitrogen cycle by making nitrogen fertilizers and by oxidizing atmospheric molecular nitrogen through the extensive burning of fossil fuels. Nitrites and nitrates, as known as NOx, are present in many impact categories, as we will see in the next sections. The process of the nitrogen cycle consists of the following steps. These processes take place in several stages and are explained below. First, nitrogen fixation. At the beginning, nitrogen is deposited into soils from the atmosphere and surface waters, mainly through precipitation. It undergoes a set of changes, promoted by bacterial organisms, in which nitrogen gets separated and combines with hydrogen to form intermediate products, typically ammonia or ammonium. Next, nitrification. In this process, the ammonia or ammonium is converted into nitrates and nitrites, a usable form for living organisms, by the presence of bacteria in the soil. Third, assimilation. Plants take in nitrogen compounds, ammonia, nitrite ions, nitrate ions, or ammonium ions, from the soil with the help of their roots. This way, the nitrogen enters the food web. We have here the ammonification process. When plants or animal die, the nitrogen present in the organic matter is released back into the soil. The bacteria decomposers convert the organic matter back into ammonium, which is further used for other biological processes. Finally, denitrification. Denitrification is the process in which the nitrogen compounds make their way back into the atmosphere by converting nitrate into gaseous nitrogen. This nitrogen cycle process is the final stage and occurs in the absence of oxygen. Denitrification is carried out by denitrifying bacterial species. Earth's water is constantly moving through the water cycle, shifting between liquid, vapor, and solid states across the surface, atmosphere, and subsurface. At first, Earth was a molten planet. As magma released water vapor, the atmosphere cooled until liquid water could accumulate on the surface. Volcanic activity continues to release water, increasing surface and groundwater volumes. The sun powers the water cycle by heating oceans, causing evaporation. Water also enters the atmosphere through sublimation, ice or snow to vapor, evapotranspiration from plants, and soil evaporation. Okay, but what happens when sun heats harder? Why do we say that global warming increases the sea level, causes floods, and changes climate? This occurs because of several interconnected physical processes. Sea level rise. Global warming leads to higher temperatures, which cause glacier and ice sheets to melt, adding more water to the oceans. Additionally, as ocean water warms, it expands. Both effects cause the average sea level to rise. Floods. Warmer air holds more moisture, leading to more intense and frequent rainfall. When heavy rain falls in a short period, it can overwhelm drainage systems and rivers, resulting in floods. Also, as more precipitation falls as rain instead of snow, especially in colder regions, rapid runoff increases flood risk. Melting snow combined with rain can further intensify flooding events. Climate change. The increase in greenhouse gases from human activities traps more heat in the atmosphere, raising global temperatures. This warming disrupts established weather patterns, leading to more extreme events such as heat waves, droughts, intense storms, and shifting rainfall patterns. These changes alter local and global climates, affecting ecosystems, agriculture, and human societies. But let's continue with our water cycle. After evaporating, vapor rises into the air where cooler temperatures cause it to condense into clouds. Air currents move clouds around the globe, cloud particles collide, grow, and fall out of the sky as precipitation. Some of it falls as snow and accumulates as ice caps and glacier where frozen water can be stored for years depending on the climate conditions of the area, or it may just melt after a few days as snowmelt runoff. Most precipitation falls back as liquid water into the oceans or onto land as surface runoff. A portion of runoff enters rivers and moves to the oceans, dragging chemicals, microplastics, and other materials along its paths, while another part accumulates and is stored as freshwater in lakes. Most of the runoff soaks into the ground as infiltration. Some water infiltrates deep into the ground and replenishes aquifers, saturated subsurface rock, which store huge amounts of fresh water for long periods of time. Notice in the next figure how from the overall water, more than 96% is saline. And, of the total fresh water, over 68% is locked up in ice and glacier. Another 30% of fresh water is in the ground. Thus, rivers and lakes that supply surface water for human uses constitute an extremely small part of all the water on the Earth. In this slide you can see a scheme showing the water cycle described previously. From the sun power evaporating the ocean, to the precipitation and water runoff returning to the sea. Let's move now to eutrophication. This is defined as the gradual increase in the concentration of plant nutrients, phosphorus, nitrogen, and minerals, in an aquatic or terrestrial ecosystem. Do you remember the natural cycle of nitrogen described in first slides? Let's see what happens when this is disturbed by human activity. Human activities related to the use of detergents, fertilizers, and other nutrient systems speeds up eutrophication. The productivity or fertility of such an ecosystem naturally increases as the amount of organic material that can be broken down into nutrients increases. This material enters the ecosystem primarily by runoff from land and as products from the reproduction and death of terrestrial organisms. Water blooms, or great concentrations of algae and microscopic organisms, often develop on the surface, preventing light from penetrating and oxygen from being absorbed, which are necessary for underwater life. Eutrophic waters are often murky and may support fewer large animals than non-eutrophic waters. Commonly, eutrophic marine systems may exhibit extremely low oxygen concentrations in bottom waters, a condition known as hypoxia. Plant growth in temperate freshwater or terrestrial ecosystems tends to be primarily limited by nitrogen and phosphorus availability, so increasing the input of this limiting nutrient often has a cascade of effects. For instance, a decrease in light at surface or soil level. A decrease in biodiversity. The nutrients that make our crops grow better also fertilize phytoplankton in lakes and the ocean. Phytoplankton are microscopic organisms that photosynthesize just like our food crops. With more nitrogen and phosphorus available to them, they grow and multiply. When the phytoplankton dies, decomposers eat them. The decomposers also grow and multiply. As they are eating all of the abundant phytoplankton, they use up the available oxygen in the water. The lack of oxygen forces mobile organisms to leave the area and kills those organisms that can't leave. Now let's examine a compelling real-world example of aquatic eutrophication through the Mississippi River case study, which perfectly illustrates how agricultural practices can create environmental impacts that extend far beyond their immediate location. The Mississippi River system represents one of Earth's most significant watersheds. As the largest river basin in North America and third largest globally, it drains over 40% of the continental United States. What makes this case particularly relevant to LCA is that 58% of this drainage area consists of highly productive farmland, creating a massive agricultural footprint with downstream consequences. The environmental transformation began in the 1950s. Since then, nutrient concentrations in the lower Mississippi River have increased dramatically, directly correlating with the intensified use of nitrogen and phosphorus fertilizers across the watershed. This temporal connection demonstrates a classic example of how industrial agricultural practices create cumulative environmental impacts over time. Here's where the eutrophication mechanism becomes critical to understand. When the Mississippi's nutrient-laden waters reach the Gulf of Mexico, they act as a massive fertilizer injection into the marine ecosystem. The excess nitrogen and phosphorus trigger explosive growth of marine phytoplankton, those microscopic photosynthesizing organisms that form the base of marine food webs. However, this apparent boost in primary productivity quickly becomes an environmental disaster. When these phytoplankton populations inevitably die, their decomposition creates a cascade effect. The bacteria and other organisms that break down this massive quantity of dead organic matter consume dissolved oxygen at unprecedented rates, creating hypoxic conditions, essentially suffocating the marine environment. The scale of this dead zone is staggering and provides a powerful illustration of how local agricultural decisions can create regional environmental impacts. The hypoxic zone in the Gulf of Mexico has grown to encompass an area 140 times the size of Barcelona. To put this in perspective, we're talking about thousands of square kilometers of marine ecosystem where oxygen levels are too low to support most marine life. From an LCA perspective, this case study demonstrates several critical principles. First, it shows how the spatial scale of environmental impacts can extend far beyond the location of the original activity. Fertilizer applied to cornfields in Iowa contributes to marine ecosystem degradation in the Gulf of Mexico. Second, it illustrates the importance of understanding fate and transport mechanisms in impact assessment. The nitrogen and phosphorus don't simply disappear after crop harvest, they follow hydrological pathways that connect terrestrial and marine systems. This case also highlights why we separate freshwater and marine eutrophication in modern LCA methods, as the limiting nutrients and ecosystem responses differ between these systems. The Mississippi River case shows how terrestrial nitrogen inputs specifically drive marine eutrophication, while phosphorus tends to be the limiting factor in freshwater systems. The economic and ecological costs of this eutrophication extend beyond the immediate dead zone. Commercial fisheries suffer, tourism declines, and the entire Gulf ecosystem experiences reduced biodiversity and altered food webs. This demonstrates why eutrophication potential is considered a critical midpoint indicator in life cycle impact assessment. It connects specific chemical inputs to measurable environmental damage with clear economic and social consequences. Now let's examine ozone depletion as a critical midpoint indicator in LCA. The stratospheric ozone layer acts as Earth's natural sunscreen, absorbing over 97% of harmful UV radiation before it reaches the surface. This protective shield began deteriorating in the 20th century due to human-made gases like chlorofluorocarbons, CFCs, from refrigerants and aerosols. The destruction mechanism involves chlorine and bromine atoms catalytically breaking down ozone molecules. A single chlorine atom can destroy over 100,000 ozone molecules before leaving the stratosphere. This creates a dangerous imbalance where ozone destruction outpaces natural formation rates. Bromine and chlorine always look for their stable forms. While ozone is continuously being depleted naturally, it is also formed. Ultraviolet light from the sun photolyzes oxygen molecules. Oxygen atoms react with molecules and form ozone molecules. Here you have the chemical reaction in case you wish to profundize into more detail. Different reactions may happen depending on the latitude we are. The ODS breaks this equilibrium, leading to diverse effects. On the one hand, increased UV radiation reaching Earth's surface, elevating risks of skin cancers, melanoma, squamous cell carcinoma, and eye damage. On the other hand, tropospheric ozone accumulation near ground level, where it becomes a toxic respiratory irritant particularly harmful to children, the elderly, and asthma sufferers. The Montreal Protocol, from 1987, represents humanity's most successful environmental intervention. Its unique adjustment provision allows rapid response to new scientific data, accelerating phase-outs of ozone-depleting substances, ODS. Universally ratified by all UN members, it demonstrates global cooperation can reverse environmental damage. Several scientific tools and procedures were developed to support Montreal Protocol efforts. For example, atmospheric monitoring to track ODS concentrations through in situ and remote sensing. Also, the midpoint indicator ozone depletion potential, or ODP, which quantifies each substance's relative damage capacity compared to CFC11, was used to quantify that. How are we doing so far? The ozone hole, which was discovered in 1985, is the result of human-emitted chlorofluorocarbons, which are ozone-depleting chemicals and greenhouse gases used as coolants in refrigerators and in aerosol spray. More than 30 countries signed the Montreal Protocol in 1987, which phased out the production and consumption of CFCs. By protecting the ozone layer, which blocks harmful UV radiation, the Montreal Protocol also protects plants and their ability to pull carbon from the atmosphere. Fortunately, and thanks to all the efforts in this matter, the recovery progress is measurable. The Antarctic ozone hole discovered in 1985 is steadily healing. Current projections indicate near-complete recovery of Arctic Northern Hemisphere ozone by 2035, with Antarctic recovery around 2060. In atmospheres containing nitrogen oxides and volatile organic compounds, ozone can be created in the presence of sunlight, which provides the activation energy. Peroxy radicals are produced. They are highly reactive and toxic compounds, and the presence of peroxy radicals can result in an increase of the concentration of ozone through a complex reaction pattern. Ozone is a secondary pollutant, as there is practically no ozone present in source emissions directly derived from human activity. This means that we do not emit ozone, but we do emit things that react and transform into ozone in the troposphere layer of the atmosphere. In atmospheres containing nitrogen oxides and volatile organic compounds, ozone can be created in the presence of sunlight, which provides the activation energy. Peroxy radicals are produced. They are highly reactive and toxic compounds, and the presence of peroxy radicals can result in an increase of the concentration of ozone through a complex reaction pattern. Ozone is a secondary pollutant, as there is practically no ozone present in source emissions directly derived from human activity. This means that we do not emit ozone, but we do emit things that react and transform into ozone in the troposphere layer of the atmosphere. In addition, that nitric acid present in the photochemical smog may cause acid rain and increase the acidification levels in land or water. Chemicals can be emitted to the environment, this is to air, water, or soil, during all life cycle stages of products, services, and systems. Emission inventories of different products may contain hundreds of chemicals, of which many will have the potential to cause toxic impacts on humans, including cancer and various non-cancer effects, leading to damage to human health. This impact category analyses effects due to different means of exposure. In example, oral intake, dermal absorption, or inhalation. This should be protected by reducing the exposure time, increasing the distance to the emission point and using different PPE protective layers. Let's look now into next example. A painter and decorator aged 40 years presented with a 6-week history of malaise, abdominal cramps, nausea, arthralgia, and mild mental impairment. He had previously been working using an industrial blowtorch and sander to remove paint. 2 of the 3 floors had timber-paneled walls, all had 8 to 10 coats of paint and some were clearly very old. Although he had acquired a new respirator, he did not wear it when other workmen were burning off or sanding in other rooms on the same floor, and during breaks he ate, drank, and smoked cigarettes in the same building. No measurements of atmospheric lead concentrations were made. The painter failed to wear his respirator during sanding burning operations, allowing lead dust inhalation. He ate, drank, and smoked cigarettes on site, enabling lead ingestion through hand-to-mouth transfer. Using dry methods, blowtorch sander, without containment amplified airborne lead exposure. No air monitoring was conducted to assess contamination levels. These actions violated core occupational safety protocols for toxic materials. The symptoms, malaise, abdominal cramps, nausea, arthralgia, and cognitive issues, are classic signs of acute lead poisoning. Lead disrupts neurological function, causing mental impairment, damages red blood cell production, leading to fatigue and nausea, and accumulates in bones or joints, causing pain. Without intervention, this could progress to permanent kidney or neurological damage. We will move now to talk about fine particles. This indicator evaluates the effects on human disease, in example, chronic long-term mortality and chronic bronchitis, due to the inhalation of fine particulate matter. There are different models and methods to estimate this effect, all of them based on exposure and fate. This impact category is measured in disease incidence. PM stands for particulate matter, also called particle pollution, the term for a mixture of solid particles and liquid droplets found in the air. Some particles, such as dust, dirt, soot, or smoke, are large or dark enough to be seen with the naked eye. Others are so small they can only be detected using an electron microscope. Particle pollution includes PM10, inhalable particles, with diameters that are generally 10 micrometers and smaller. PM2.5, fine inhalable particles, with diameters that are generally 2.5 micrometers and smaller. These particles can be made up of hundreds of different chemicals. Some are emitted directly from a source, such as construction sites, unpaved roads, fields, smokestacks, or fires. Most particles form in the atmosphere because of complex reactions of chemicals such as sulfur dioxide and nitrogen oxides, which are pollutants emitted from power plants, industries, and automobiles. Inhalating these particles can get deep into the lungs and some may even get into bloodstream. Its exposure paths are the same as those mentioned in human toxicity, but its mechanism goes differently. Not necessarily toxic chemicals but fine particles which affect mainly the respiratory system, irritating lungs, throat, or lungs. Let's examine a compelling case study from Poland that illustrates the real-world impact of fine particulate matter on human health and demonstrates the importance of proper monitoring strategies in LCA assessments. This research focused on PM10 measurements in 2 major Polish cities, Wroclaw and Cracow. The selection of these cities wasn't random. Each represents distinct pollution challenges that help us understand how different urban environments affect particulate matter distribution. Wroclaw was chosen due to its characteristic dense urban architecture, featuring predominantly old tenement houses and estates of single-family homes. This city experiences particularly severe air pollution during autumn and winter months, making it an ideal case study for understanding seasonal pollution patterns. Cracow presents a different challenge altogether. As Poland's most polluted city, its environmental problems stem largely from geographical factors. Located in the Vistula Valley and surrounded on three sides by elevated terrain, Cracow experiences a phenomenon where polluted air becomes trapped over the city rather than being naturally dispersed by wind patterns. The health implications are staggering and directly relevant to LCA impact assessment. According to WHO data from 2016, 91% of the global population lived in areas exceeding air quality guidelines. In Europe alone, approximately 440,000 people die annually from air pollution, with Poland accounting for 44,000 deaths, representing 10% of Europe's air pollution mortality despite having only about 7% of its population. Now, here's where the study reveals critical insights about particle size distribution. The measurement showed that small diameter particles less than 0.3 micrometers predominated, with about 99% of measured particles being smaller than 1.0 micrometer. This finding is crucial because these ultrafine particles bypass the human body's natural filtration systems and penetrate directly into the respiratory system, where they can cross into the bloodstream. The measurement locations were strategically selected near both highway and railway infrastructure, capturing emissions from trains and diesel locomotives. This multi-source approach demonstrates how LCA practitioners must consider the cumulative effects of different emission sources in their assessments. An interesting meteorological observation emerged during the Wroclaw measurements. The study period coincided with heavy morning rainfall, which created an unexpected natural experiment. Can you predict whether higher particulate matter concentrations were found during morning or afternoon measurements? Counterintuitively, the highest concentrations occurred during the rainy morning hours in Wroclaw. This finding initially seems paradoxical. Shouldn't rain clean the air? The researchers discovered that rainfall intensity and accompanying wind patterns actually increase particulate matter emissions in the short term. During rainfall, they observed large numbers of solid particles in terms of both mass and particle count. However, the story has a twist that reveals the complex dynamics of atmospheric chemistry. While rain initially mobilized more particles, the overall effect was air cleaning. The morning precipitation was ultimately effective in reducing particulate matter concentrations. This demonstrates the importance of understanding both immediate and longer-term atmospheric processes in LCA modeling. Interestingly, Cracow showed similar concentrations between morning and afternoon measurements, suggesting that the geographical trapping effect in the Vistula Valley creates more consistent pollution levels regardless of meteorological conditions. This case study exemplifies several critical principles for LCA practitioners. First, it shows how spatial factors, urban morphology, topography, and geographical location, significantly influence pollutant fate and transport. Second, it demonstrates that temporal variations in emissions and meteorological conditions must be considered in impact assessments. Finally, it highlights how measurement location and methodology can dramatically affect the data used in LCA studies, emphasizing the need for representative sampling strategies. The implications extend beyond academic interest. This research revealed that official monitoring stations often underestimated actual exposure levels, sometimes by factors of 2 or more, highlighting the importance of comprehensive environmental monitoring in supporting accurate LCA assessments. Resource depletion occurs when renewable and non-renewable natural resources become scarce because they are consumed faster than they can recover. The term resource depletion is commonly associated with water usage, fossil fuel consumption, trees, and fishing. All these resources have been depleted primarily because of human activities. The cycles and equilibriums described in all the previous impact categories existed since before human activities increased since the industrial era. Therefore, the main causes associated with the depletion of resources are overpopulation, poor techniques, overconsumption, and deforestation, among others. The Product Environmental Footprint, PEF, evaluates 2 impact categories in depletion of resources. First, the resource use of fossils like oil, which is an essential commodity in manufacturing, planting, mining, and transportation among many activities, and its depletion would be devastating. This indicator evaluates the use of resources with energy carriers from fossil fuels, using a reserve base as a reference for resource stock. This impact category is measured in abiotic resource depletion fossil fuels, or ADP fossil, and expressed in megajoules. We also have resource use of minerals and metals. There has been an increase in the exploitation of minerals such as phosphorus, copper, and zinc among others to sustain the 7 billion people on Earth. This indicator evaluates the use of mineral and metal resources, using reserve base as a reference for resource stock. This impact category is measured in abiotic resource depletion, ADP ultimate reserves, and expressed in kilogram of antimony equivalents. We have another example for this topic. This is the Alberta's fossil fuel extraction story. This case study perfectly illustrates the fundamental principles of exponential depletion that govern all finite resource extraction. Alberta's oil extraction began during World War I, when the province served as a major supplier to Britain. However, production remained sporadic until after World War II, when the ensuing oil boom transformed Alberta into Canada's fossil fuel hub. The graph shows a dramatic acceleration starting in the 1950s, with production peaking in 1998, a critical inflection point that demonstrates how resource extraction follows predictable depletion curves. What makes this case particularly fascinating is the dual nature of the extraction pattern. You can see both oil and gas production rising together, but notice how gas production continues growing even as oil production plateaus and declines. This reflects the geological reality that natural gas often remains accessible even after oil reserves become economically unviable to extract. The human behavior aspect of this depletion follows what researchers Ugo Bardi and Alessandro Lavacchi describe as predator-prey dynamics. In their groundbreaking analysis, they argue that humanity's extraction of fossil fuels represents a special case of these biological interactions. We become the predator, and fossil fuels become our prey, but unlike biological systems, our prey cannot reproduce. This relationship follows the Lotka-Volterra model, which typically simulates boom-bust cycles between predators and prey in nature. However, when applied to fossil fuel extraction, the model reveals a troubling asymmetry. While biological prey populations can recover, depleted oil and gas reserves cannot regenerate on human timescales. The mathematical reality underlying this process is stark. Exponential growth directly links to exponential depletion. This follows from simple conservation laws. If you want your stock of A, in this case, human population and economic activity, to grow exponentially, you must deplete your stock of B, fossil fuels, at an exponential rate. There is no alternative within our current energy paradigm. When we examine the mathematical formulation, energy consumption follows. Y equals 1 plus R to the power of T, where T represents time and R represents the fractional growth rate. For exponential depletion, we simply make the growth rate negative. Y equals 1 minus R to the power of T. This elegant mathematical relationship explains the production curves we observe in Alberta. EROI tells us about the declining efficiency of extraction over time. In Alberta's case, the EROI has fallen dramatically from approximately 1,200 barrels return per barrel invested in 1919 to just 5 barrels per barrel invested by 2007. This represents a 99.6% decline in extraction efficiency over less than a century. Think about what this means. In 1919, for every barrel of oil energy you invested in exploration and extraction, you received 1,200 barrels back. By 2007, that same investment yielded only 5 barrels, barely above the minimum threshold needed to maintain industrial civilization. This declining EROI reflects the fundamental physics of resource depletion. Initially, you extract the easiest to reach, highest quality resources. Alberta's early oil wells tapped into shallow, high-pressure reservoirs that practically pushed oil to the surface. As these deposits depleted, extraction moved to deeper, more complex formations requiring advanced drilling techniques, hydraulic fracturing, and eventually oil sands processing. The implications extend far beyond Alberta. Research shows that the global EROI for oil production has declined from roughly 24 in the 1950s to approximately 11 by 2007. This creates an exponential relationship between EROI and oil prices. As energy return decreases, the economic cost of extraction increases exponentially, not linearly. From an LCA perspective, this case study demonstrates several critical principles. First, it shows how temporal dynamics fundamentally alter the environmental and economic footprint of resource extraction. The same oil field that had minimal environmental impact per barrel in 1950 requires dramatically more energy, water, and land disturbance to extract the same amount of oil today. Second, it illustrates the concept of depletion gradients, the idea that resource extraction follows predictable patterns where quality and accessibility decline over time. This has profound implications for life cycle assessment, as the environmental impact per unit of extracted resource increases throughout the lifetime of a deposit. Finally, Alberta's story reveals the interconnected nature of resource depletion and technological development. As conventional resources depleted, the province shifted toward unconventional extraction methods like oil sands processing, which requires vastly more energy and water per barrel produced while generating significantly higher greenhouse gas emissions. The broader lesson for LCA practitioners is that resource depletion is not simply about running out of materials, It's about the escalating environmental and energetic costs of accessing increasingly marginal resources. This case study shows why depletion indicators in LCA must account for both quantity and quality degradation over time. As the previous study concludes, in the game of future envisioning, fossil fuel depletion is the known. We know that fossil fuels are finite, and that we will run out. Existing renewable technologies are the known unknown. We know they work, but we don't know if they, alone, can support our current industrial society. And the unknown unknowns are everything else. Finally, we will end this presentation talking about land use. This is the term used to describe the human use of land. It represents the economic and cultural activities, e.g., agricultural, residential, industrial, mining, and recreational uses, that are practiced at a given place. Public and private lands frequently represent very different uses. Land use changes occur constantly and at many scales, and can have specific and cumulative effects on air and water quality, generation of waste, extent and quality of wildlife habitat, climate, and human health. Agriculture is a major use of land. Half of the world habitable land is used for agriculture. The extensive land use has a major impact on the Earth's environment as it reduces wilderness and threatens biodiversity. Reducing the consumption of resource-intensive products and increasing the productivity of land makes it possible to produce food with much smaller inputs and reducing the impact on the environment. The world map before you reveals striking patterns in agricultural land use distribution across the globe. The darkest green areas represent countries with the most extensive agricultural footprints, over 250 million hectares. Notice how China, India, the United States, and Brazil dominate this category, reflecting not just their large territorial sizes but also their roles as major food producers for global markets. This visualization illustrates a fundamental challenge in LCA. Agricultural land use accounts for half of all habitable land on Earth. When we assess the environmental impact of food products, we're dealing with the planet's most extensive human land use activity. The lighter green areas, representing smaller agricultural footprints, often correspond to countries with different climatic conditions, population densities, or economic structures. What's particularly significant from an LCA perspective is that land use intensity varies dramatically across these regions. A hectare of agricultural land in the Netherlands produces vastly different environmental impacts compared to a hectare in Mongolia, due to differences in farming practices, inputs, and ecosystem contexts. Now, let's explore three critical concepts that complicate land use decisions in our modern world. First, the not in my backyard or NIMBY phenomenon in renewable energy production. This concept reveals a fascinating paradox. While communities support renewable energy in principle, they often resist having wind farms, solar installations, or bioenergy facilities located near their homes. From an LCA standpoint, NIMBY creates spatial displacement of environmental impacts, pushing renewable energy infrastructure to areas with less political resistance but potentially greater ecological sensitivity. Second, the biodiesel land use dilemma perfectly exemplifies the food versus fuel debate. First-generation biodiesel production requires substantial agricultural land, often competing directly with food production. Consider this striking reality. Producing enough biodiesel to replace just 10% of global diesel consumption would require converting millions of hectares of additional land to oil crop production. This creates indirect land use change as food production gets displaced to other areas, potentially causing deforestation and habitat loss. The LCA implications are profound. While biodiesel offers lower direct carbon emissions compared to fossil diesel, the land use change emissions can completely offset these benefits. This demonstrates why comprehensive LCA must account for both direct and indirect land use effects, a principle that has revolutionized how we assess biofuel sustainability. Finally, vertical agriculture emerges as a potentially transformative solution to land use pressures. This technology involves growing crops in vertically stacked layers, often in controlled environments using hydroponics or aeroponics. The space efficiency is remarkable. Vertical farms can produce 100 times more food per square meter compared to traditional agriculture. However, from an LCA perspective, vertical agriculture presents interesting trade-offs. While it dramatically reduces land use and eliminates pesticide needs, it requires significant energy inputs for LED lighting and climate control. The environmental benefits depend heavily on the carbon intensity of the electricity grid powering these facilities. Vertical agriculture also offers unique advantages for urban food security, reducing transportation distances and enabling year-round production regardless of climate. This could significantly alter the land use footprint of urban food systems, potentially reducing pressure on rural agricultural land. These concepts highlight why land use represents one of the most complex midpoint indicators in LCA. Unlike emissions that disperse into global atmospheric systems, land use impacts are inherently local and context-dependent. The same crop grown in different regions can have vastly different biodiversity, soil quality, and water resource impacts. The challenge for LCA practitioners is developing characterization factors that capture these spatial variations while remaining practical for widespread application. This requires balancing scientific rigor with data availability, an ongoing challenge in the field of land use impact assessment. So we arrive to the end of this course. Understanding the chemical principles behind LCA midpoint indicators empowers us to make more informed choices for a sustainable future, connecting the impacts of our actions to the health of our planet and society. Feel free to leave a comment or reach me out directly through my social media in case you need further training or collaboration.